Hello and welcome back to Calculus 1, section 311, related rates. The key is the word rate, and then it's plural. So it has the S at the end. That means few of those. Rates imply derivatives. We know those, rates of change. And then we also have the word related. They will be related through a formula. Now, this is highly applicable stuff. We'll see all of the problems are word problems. So I want to start with a very simple problem. Behold a square, right? Now let's say this square is made out of very thin metal sheet. And let's say you heat that metal. What happens is all of the sides grow as you heat the material, and it becomes larger. So now we have a rate of change of the length of the side. We have rate of change of perimeter. We have rate of change of area. If the old square had the side of length A, then the area was A squared and the perimeter was 4A. Now, whatever phenomena we are observing is going to change in time. And I'm going to write this in blood. Change happens in time. Change happens in time. That is the derivative in respect to time, d dt. So, as I heat this metal, which is in the shape of a square, very thin, think of it as a paper, right? Just a square, and it's made out of metal, so it expands as you heat it up. I can ask for the rate of change of perimeter, I can ask for the rate of change of area. Well, you will start with the perimeter formula, and you will differentiate it in time. The derivative of P is 1, and then you have dP dt on the chain rule. Remember that you are taking the derivative of a variable which is changing. Clearly the perimeter is changing because the square is becoming bigger. Bigger square, bigger perimeter. So perimeter is the variable, and if you differentiate that in respect to time, which is a different variable, you have a dimension mismatch, which means you have to follow by the chain rule. So the derivative of P is 1 in respect to t, but then you have to follow with dP dt. That's the chain rule part, in place of differentiation. On the other side, you have 4. Derivative of A is 1, and you follow with dA dt. This formula here is called related rates. You have a rate of change of perimeter and the rate of change of the length of a side, and they are related by times 4. To answer the second question, I have that the area is equal to a squared. I hit this with the derivative in time, and I get the rate of change of area in time is 2a dA dt. This is also related rates. As you can see, the formula is now different because we were working on a different concept. Now I give you the values of things that I can observe and measure, and you can calculate the rest. If you are in a lab and you have the square, you can set this square against some kind of a scale in the back, and then you observe and you see that after 1 minute of heating the metal sheet, it expanded so many units. That gives you the rate expansion of the length of the side. So that gives you dA dt. And you can calculate dP dt at that point. You can calculate dA, the change in area. So if you have something that you can measure, which is what is given to you in a text when you read the word problem, then you can compute other aspects. They gave immediately the problem of oil rig. Right? We remember the BP, wasn't that far along, right, ago, when BP spilled all the oil, right, all over the ocean. So what you have is you have this, looking at the ocean, right, this point-like speck oil rig, right, and it leaks oil, right, starts leaking oil. So the oil will spread in a circle, 360 degrees in radius, right? 360 degrees around oil rig. And in time, it grows. Covering more and more square miles, which is obviously environmental disaster. So now, you can measure the radius. You can also measure how fast it's spreading, because you say, okay, it went 1 mile out, and I waited another 30 minutes, it went another mile out, and I waited another 45 minutes, and now it's another mile out, and so on. So you can measure certain things about this. So you have oil rig, and you have this oil spill that is going to make these concentric circles grow. It's obviously taking the surface area. Now, it costs money to clean it. And it costs money, right, per square mile. So you are going to start computing, right? And what you have, this says, an oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at the rate of 30 meters per hour, you see, the radius of the oil patch increases at the rate. That's dr dt. Another clue that you have are units, meters per hour. You see, r is the length, radius, right? And that's in meters. T is time, and that's in hours. So the rate at which the length of the radius changes is 30 meters per hour. So that has to be dr dt. You have to be able to pick that up. How fast is the area increasing when radius is 100 meters? Radius is 100 meters. And now they're asking how fast is something changing, area. Well, the way to write how fast is to take derivative in time. So they're asking for change in area, so dA dt. So this is what we have. This is the information that is given to us in the text. We are dealing with a circle. We are getting the rate of change of radius in time, which is 30 meters per hour. And we know that we are already 100 meters out from the radius. That's the radius. That's 50 times my height. I'm almost 2 meters tall. So that's 50 times my height around the radius. And then you have the how fast. So this d dt is how fast in words. How fast is the area changing? Now, you look at the stuff that is there. They're talking about the area of a circle. Your Calc1. What is the area of the circle? Pi r squared. Can I use this formula to somehow get the rates? What should I do? This is the formula we have. These are the concepts that we need. How do I connect those two things? Yes? Beautiful. Take the derivative in respect to time. You will always take derivative in respect to time in this section. So now, derivative of a is 1, dA dt. We are doing implicit differentiation now. Pi is a constant, copy that. Derivative of r squared is 2r, and then dr dt because of the dimension mismatch. Again, chain rule or implicit, whatever you want to call it. So change in area in time is 2 pi r dr dt. Well, they tell you that r is 100. They told you that the change in radius is 30. So when you plug all of those in, you have 6,000 pi meters squared per hour. It's area divided by time. So that's almost 18,000 meters squared. If I use myself as a measuring unit, so I put myself vertical and put one more horizontal, it's going to be 4 meters squared. Because 2 times 2 is 4, right? Look at that, 18,000 meters squared per hour. That's huge, right? Not huge compared to us. There are things out there, the distances and speeds that make us so insignificant in every aspect. It's amazing. What?
What's the derivative of pi?
What's the derivative of pi? Why?
Oh, yeah, 2.6.
Because pi is 3.14 blah blah blah, the derivative of a constant is 0. If it's a constant over there, we copy it. Good. All right. So Math Club recently took on the project to work on drones, and they will be building a drone and a few other projects, and they also have invitation by the regional airport Hillsborough to fly the drones, and then also, you know, take a look at airplanes and things like that. So now, what we want to do is we want to take a look at related rate problem with the converging airplanes. So here's the airport, and we have one airplane coming from the south and one airplane coming from east. So the south is going towards north, obviously, and the one from the east is going west. So there's the airplane right here, and then there's the airplane right here. It shouldn't be nuclear physics for you to understand that the distance between these two planes as they progress forward will be decreasing, right? And what we definitely don't want to happen is for that distance to become zero. What happens if the distance between two airplanes is zero? Exactly, fireworks. We don't want that. So, yeah, it's just one shot. Terrible. So, we have the air traffic control, and they make sure that that stuff doesn't happen. Now, this is going to follow these two airplanes. It says two planes are on approach the airport, one flying due west and 120 miles per hour, and the one going north is 150 miles per hour. And they want to know how fast is distance between them changing. Maybe I should put capital D here. So this is distance over here. This is distance between the planes. So how fast is distance between the two planes changing? How should I write that? What am I looking for? How fast is the distance changing? Nice. Nice. How fast is distance changing? When westbound plane is 180 miles away and the other guy is 225 miles away. Great. How do you propose to do this problem? We have, now the key for all of these problems is to look at the type of the geometry you have in front of you.
Pythagorean Theorem.
So we have a triangle. You said Pythagorean Theorem. What do you say? Same thing, Pythagorean Theorem. So what do we have as concepts for triangles? We have the 6 trigonometric functions. We have area, we have perimeter, we have Pythagorean Theorem. So you start eliminating things. Do we have any angles? Do we have to worry about angles? The answer is no. 6 trig functions out. Do we care about the area? No. Out. Do we care about the perimeter? No. Out. The only thing that is left is Pythagorean Theorem. Alright, so Pythagorean Theorem should play a role. But also, there is this concept of a distance, right? So we can use also distance formula, which would give us the same thing as Pythagorean Theorem. Now, I need to label the rest. I have 180 miles, and I have 225. we're going to agree that this side is y, because that's the vertical as we look here, and this is x. So the first equation we can write is the one that you all want, which is x squared plus y squared is equal to d squared. Now we also have this 120 miles per hour. How do I write that in terms of mathematical variables? What is 120 miles per hour? Yeah, but what is as a concept, and then eventually to find the variable that we have to use? Okay, speed. So what is that related to? The what? The derivative of what? Position. And now what's the position for this airplane? Measured by? I can't hear you. Air conditioning is on. Well, you can't take derivative of 180 miles. What is the variable that describes the point where the airplane is? X. So we have that the dx dt is 120 miles per hour. And you have x to be 180. And over here you have dy to be dy dt to be 150. And y to be 225 miles. So now, if I take the equation that we all agreed upon and differentiate in terms of time, I will get all of the variables that I need to solve the problem. What's the derivative of x squared with respect to t? Nice. What's the derivative of y squared with respect to t? Nice. And what's the derivative of the distance between two airplanes in respect to t? Great. If you stare at what you have and what you need, you should be able to solve the problem quickly. Do I have x? Yes, I do. Do I have dx dt? Yes, I do. Do I have y? Yes, I do. Do I have dy dt? Yes, I do. I am looking for d dt, so we're not going to worry about it. I am checking that as I have it, because that's what I'm looking for. The only thing that I don't have is a capital D. Everything else is there. What should I do for capital D? Yes. Take the Pythagorean theorem between x and y and figure out how much D is. So you will have to do this from time to time in these problems. So we are going to do Pythagorean theorem. We already have that formula up there. We are going to use x and y, 180 and 225, grind through whatever numbers we get to get D, and then we have D. We can feed everything in a formula and get d dt. And what do we get for D? $288.14, everyone? Beautiful. And now First of all, I don't know if you see this, but all of these 2's die. And if you divide the entire equation by 2, they're all gone. All right, so now what's the value of x? 180. What's the value of dx dt? 120. Plus, what's the value of y? What's the value of dy dt? Equals to 288.14 times dd dt. And you see dd dt is the thing that we're looking for. So, not a problem. dd dt is equal to, you compute all of these guys. So what do we get when we compute the left hand side? And divide that by 288 by 14. What do we get for this calculation? 180 times 120. And then plus the rest. 190.
I'm just giving you the final answer.
I need a number on top. 55350. All right. So if one airplane is going 150 miles per hour and the other one is going 120 miles per hour in relation to each other, they are getting closer at 192 miles per hour between them. So let's see. Ready? This is live. It is the Flight Radar 24. Aircrafts 1,115 out of 13,818. So I guess what they show against what's in the air.
I've never actually thought about that.
So, do you think that there is a human sitting figuring out these related rates that we just have for 2 airplanes coming in when you have 15 of them trying to land and take off at the same time? These are your jobs. You understand the problem with 2 airplanes, then you learn linear algebra to get the matrix of things, and then you learn computer science to program that so computer can handle this. You don't sit with a paper and a pencil and try to get the thing when someone tells you, oh, I'm low on fuel because there was a lot of headwind and, you know, because sometimes you can't predict. I mean, yeah, you start off with a full plane and stuff, but things happen. And you go on the other side, right? It's this is what the job is. And you know what's the great thing? A lot of jobs are coming up in air traffic control, pilots, and all that. They need a huge shortage. I found that at the airport, actually. They're trying to now start the programs and train a lot of pilots because they're needed. Look at that. And the software for this needs to be written and tested and worked out. You can clearly see the geodesic at work over there, which is the line of the shortest path between US and let's say England is going to be this line over here. That's a little bit of hyperbolic math there, but the problem we just did is done on a massive, massive scale with thousands of airplanes at once. And you have to figure out the code that will do that without mistakes, without crashing, without, right? And those are the jobs. That's your job. You want to be computer science? Well, that's what you'll be writing. Stuff like that. Now, you clearly have to know what we covered here as the first step to untangle two airplanes, because the computer keeps track of their approaches, right? And then you bring in the third dimension because, right, stagger them, and so on. Another type of mathematics to work out the landing and takeoff schedule, to work out who goes where and so on. So it's one huge, huge, huge math puzzle that has to be untangled in order for us to have whatever they believe is enjoyable flight. And you can follow with the website any plane at any given time. I'm not sure. Let's see. So you pick.
I'm gonna freak my friend out when he comes back from Japan.
Is this still the thing? Yeah, that's still the thing.
Okay, that's kind of freaky.
Yes, that's still the thing. All right, cool. So there's that as well. So yeah, you can actually subscribe to this, and I have more features if you want to. This is all live, so if I have anyone, flying to US, I don't call to check up on landing things and go online. It's just follow on the app, and then when they land or about to land, that's when I leave my house. So I don't have to wait for. Also, when you're going somewhere, right, the same airplane turns around and goes back. So let's say you want to go to Aruba or something, right? The same airplane that is going to take you there has to come in first, land, and refuel and do that stuff. So go sit on the airport 10 hours. Yes. So yeah, that's that. So those are some of the introductory examples that I wanted to do, so you guys can see the application. All of the problems in this section are word problems. We are going to do much more of this next class. I just wanted to introduce this so you can work on your lab. You have 45 minutes to work on the lab. I also need to know, is the lab due today? Lab 2. Because it's either everyone is handing in or no one is handing in. I can't do the partial thing because I will lose it, put it in a different file, not find it, and then... Is the lab due today or no? No. Okay. Lab is due when? Lab is due next week. Whose lab is this? You just need to bring it back. You don't have to touch it. Why is a question mark here? Who's George? George dropped? So just make sure you don't lose that, because I most likely will. All right, so that's it for this lecture. We'll have a part 2 on related rates next Saturday, and we'll do the review, and the quizzes will start whenever you tell me the date. Well, actually, wait. We didn't talk about the date yet. Let's talk about the date.
We kind of did.
Kinda did?
Yeah, we